This is 4.6, modeling with exponential and logarithmic functions. So we're finally going to look at some application solving exponential and logarithmic equations. We're going to be working backwards. So instead of starting with the interest problem that gives us all of the money and rate and time, we're going to work backwards and we're going to figure out how much time or what would the rate have to be in order for me to have this much money. How much time will it take for this bacteria to double? How much time will it take for this disease to infect this many people? Okay? So, we're going to start with a gross bacteria problem. And if you're starting with a single little piece of bacteria, okay, and every hour it cuts itself in half. Okay, so it started out with just one piece, it turned into 2 and 4 and so on, okay? After every hour, it just keeps doubling. Anytime you see something that says doubling, you're going to think 2 to, the x or t or whatever, okay? Doubling is 2 to the something. If it's tripling, it'd be 3 to the something, okay? If something is actually getting smaller, you can do like a half, okay? So this problem, if I'm starting with just the one piece of bacteria, okay, I'm going to do 1 times 2 to the t. Now, what would the equation be if I'm starting with 10 bacteria? And same situation, still doubling, but instead of having at times 0, I'm having 1, I'm having 10. And then that would turn into 20, and so on, okay? Well, the equation would be 10 times 2 to the t. So whenever you start with, that number goes here. If it's doubling, tripling, or if it's being cut in half, whatever that number is goes here. Okay, so we're going to look at some more application problems just like that. Not everything is that simple where it just says it's doubling or tripling, or there may be something else going on. So here's your formula so we have a new formula where we have n sub 0. Anytime you see something with a sub 0, that is your initial amount of whatever. Okay, so you have initial velocity, v sub 0. And then we've got 2, because this is our doubling time formula, time divided by A. Okay, the important thing is that these are measured in the same unit. So you don't want like minutes and then hours. You want minutes, minutes, hours, hours, days, days. Okay, so we're going to look at a bunch of examples. So this first one says, about bacteria, and it's talking about doubling. So that lets me to use this formula. It's doubling every 3 hours, and there are 1,000 bacteria in a colony. So we're going to do 3 things. We're going to find a general equation for that using our new formula, and we're going to figure out how many bacteria there are after 15 hours. This is really what we did early on in the sections. And then we're going to get into the newer stuff where I'm actually going to work backwards and use my algebra skills to solve. Okay, so what I want you to do is think for a second about what an equation would look like with this scenario using that formula. Hopefully you're thinking 1,000 times 2 to the t over 3. That's my generic equation. Now, if I know that if I want to plug in the time as 6 hours, I plug in 6. If I want to know how much bacteria there will be after 15 hours, like in problem B, then I'm going to plug in 15. So go ahead and plug in 15, and you could probably do that part of that in your head because you know that 15 over 3 is 5. Just take a second, type that into your calculator, and you should get 32,000. Okay? So this stuff is kind of the older stuff. Now here's where we get into the newer stuff. Using those skills from last time. What I want to do is set my equation right here, 1,000 times 2 to the t over 3. I want to set that equal to 100,000 for part C, because I want to know what the time has to be in order for that to happen. And I don't want to just sit there and plug in numbers for t, so I'm going to use algebra. And I'm going to divide both sides by 1,000. And the nice thing about working with things with zeros is you can just cross out the zeros. So that becomes 100. So we've got 2 to the t over 3 equals 100. Okay? Well, anytime you have a variable in your exponent, you want to take the log on both sides, or ln on both sides. So I'm going to do log. That allows the t over 3 to come down. And I actually know that log 100 is 2. So what we're going to do now is I'm going to solve for t. I'm going to get rid of everything that's around t. So there's two things bothering it. I need to multiply by 3, and I need to divide by log 2. It really doesn't matter what order I do it in. So I'm going to multiply by 3, and I'm going to divide by log 2. So I'm going to take 2. I'm going to divide by log 2. And then I'm going to multiply by 3. And I get 19.9. Okay, so that's how many hours it would take, almost 20 hours, for the bacteria to reach this much. That's kind of crazy considering that at 15 it was only 32,000. So it shows you how quickly something can add up when you're doubling it. Hey, here's another example, population. So take a second, read through the problem, try to set up an equation for this. Okay, so looking at starting with the initial amount. Okay, so we look at what we have for our initial amount, and then we're going to look at, we want to know 1 year, which is 12 months, how many were introduced to the island. Okay, so what we're going to do is 4,100 is how many were there after 8 months. So we're going to use this equation here to find out what n sub 0 is. Look in 8, 4,100. Okay, so what I need to do is divide 4,100 by 2 to the 8/3. You can just do this all on your calculator. Okay? So the initial amount would be 645.7 approximately. When you're talking about people or something that's living, or even how much of something that you can buy, you don't want to round up. So we'll just say 645. If you want to, this is your initial amount. If you want to figure out how many would be there in 12 months, what you could do is start all over again by plugging in 645 for your initial amount. Okay? So it's really about reading this problem carefully, because the first time I read it, I'm really bad about just looking at the numbers and assuming what they mean. And so when I look at 4,100, I think that's my initial amount, but it's actually not. It's how many is there after 8 months. So we actually figured out the initial amount, which is 645, and do 2 to the, if I want to know after 12 months, I'm just going to plug all of this in. 645 times 2 to the 12 over 3 is 4. And there's my answer. So that's kind of crazy that it grows that fast, but if you're doubling that often, you're going to end up with a lot. so here is a different formula. It's very similar to the last one. This is for population, but if it says relative, that's the key word, okay? So it's all about looking at details with these. So let's just look at a couple of examples. Okay, so we're talking about bacteria again, because it's so fun. And this time, I see the word relative. So that makes me go back to this formula. N sub 0 e to the RT. So we had PERT, P times e to the RT. Now we have NERT. Okay, so what I'm going to do is find all of those variables. So looking through this word problem, I've got the initial amount I'm starting with, that's my 500. I've got a rate, so my R is 40% to move the decimal over 2 places. So if I want to find the equation that represents that, all I have to do is plug in my initial amount and my rate. E is just E, and the time is going to change. So in part B, all you have to do is plug in 10 and work it out. Part C, like I said, this is the newer stuff where I'm actually going to use my algebra skills to solve. So I'm going to take my equation that I came up with, and I'm going to set that equal to 80,000. Have your calculator close by. We're going to divide both sides by 500. So I think that is 160. Yeah, that's right. So 160. Then we're going to take ln on both sides. Ln and e cancel each other out, so I get 0.4 t. And now all I have to do is divide both sides by 0.4. So ln of 160 divided by 0.4 is 12.69. So when will the bacteria reach 80,000? After, 12 hours, almost 13 hours, okay? All right, what you're going to do is try this one on your own. Think about it just for a second and be careful because this is in minutes, okay? So what I want you to do is think about what that would be in hours and then play it when you're ready to see the answer. See if you're right. Okay, so 40 minutes out of 60 minutes, which is 1 hour, reduces to 2/3. So 40 minutes is 2/3 of an hour. Okay? In our formula, we're going to take time and divide it by that 2/3. So what happens when you divide with a fraction, it flips and multiplies. So you're going to end up with 10,000, that's my initial amount, times 2, because it's doubling, to the 1.5. Okay? So again, when you're taking the time and dividing by 2/3, you flip and multiply. And 3/2 is the same as 1.5. You can write it either way. So now you're going to find another equation using this formula. If it was a relative problem in terms of E, okay? So n sub 0 times e to the RT. Your n sub 0 is the same thing. E is just E. Your R, so in the second one, we have to find R. So what we're going to do is we know that it's doubling. So in order to find the rate, we're going to take 20,000 and set that equal to 10,000 E times R to the 2/3. And we know that our time, we know what our time is, but we don't know what the rate is. So what we're going to do is we're going to use our algebra skills to solve. So we're going to divide both sides by 10,000.